A very good morning and welcome back. So we're starting a new section of the course. We last week we talked about diffusion, and that may have seemed somewhat abstract. And what we're going to do now is we're going to really lean into biological phenomenology, and we're going to exploit the obviousness of the kinds of questions that are left for us as we look at the world around us. I'm a real fan, as I've already mentioned, of dynamics, the fact that the world changes. And one of the interesting kinds of change is the existence of patterns like those seen on the left. I love satellite images, whether it's of hurricanes, although I tend to like these even more, which this is from Baja, California, if I remember correctly, or maybe it's off the coast of Chile, actually, where what you see is, you can tell which direction the wind is going. The clouds are passing an obstacle, which in this case is an island, and what you see is the wake, basically. So it's moving up is the direction of flow, and basically vortical structures are being shed off of the island, and you can see that in the wake. So, that thing for sure it calls for some sort of response intellectually. And then on the right hand side, that's the kind of thing that, I love to see. Find that one of the most prominent places that I see this is in flying over the middle of the United States, often over Kansas, Nebraska, and states like that in summer. You see these beautiful streets of clouds, which are convective rolls. And so, the notion of biological pattern is one that's so very evident. And I think, in order to give this vignette, I can't do it without acknowledging, my many friends and co-authors. Sorry, I was blocking Christina there, but so bottom line is that what I'm going to tell you about today is primarily the result of conversations with, starting at the top left, that's Yanni Kondev in Norway, and then Julie Theriault, and the lower left is Wallace Marshall, and then upper right is Hernan Garcia, and the middle Thomas Lequi, who I just talked to 10 minutes ago, and then the last one is Christina Hishen. And basically the six of us have been involved in the writing of four distinct books. Physical Biology of the Cell, The Principles of Biological Shape, The Restless Cell, which is about active matter, and Physical Genomics, which is about transcription. And one of the abiding themes of all of that work that we've done together, I think, is passionately illustrated, especially by Thomas and Julie and Wallace and Christina, where they like to call my attention to the exotic nature of biological pattern. And this is a theme that goes back, endlessly to Van Leeuwenhoek, but especially in the last 2 centuries ago now to Haeckel. So anyway, what I want to do is here I just want to give a little bit of a gallery. And the gallery, I'm not going to spend much time on names or anything like that. The gallery is for us to just really accept Darwin's words from, this is the last paragraph of the, or part of the last paragraph of the On the Origin of Species by Darwin. There is grandeur in this view of life, with its several powers having been originally breathed into a few forms or into one, and that whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning, endless forms, most beautiful and most wonderful, have been and are being evolved. So, I'm basically here now to just give you a sense of the scales of things and the nature of morphologies that arise. So, here you see the characteristic patterns of branching morphologies. And, we're familiar with this in the context of neurons. In the bottom right, I'm guessing that this is Physarum. I can't quite remember, but it's a very, very interesting organism. We know about this in the context of our lungs. We know about this in the context of our blood vessels and so on. So branching morphology is a very common thing. This is a gallery that's just meant to remind us, if you look at G, that's coral, and E is something that I would see actually right out my window, the kinds of patterns we see here in the sort of desert southwest of cacti and at the upper left you see a beautiful example of tortoise shell and then jellyfish, and I don't even need to comment on it. I'm mainly showing it because I want to make sure that we stop and notice and that we wonder. We just don't look at things and then just say, yeah. And this is more examples. The part C is one that we'll likely talk about, which has to do with gut folding. Beautiful work from Tabin and Shire and Savan and Mahadavan and others. And I'll be interested in commenting on what it takes to actually get a fold. Where do folds come from, and how do we think about them? It's a really fun thing to think about folding. So Wallace Marshall loves to put together these, what you might call, ode to non-model organisms, and to remind us of the regularity but complexity of various kinds of shape. Really super interesting. And some of those I'll show you the names of in a little bit. There's a really interesting book by Stephen Jay Gould called Wonderful Life. It's basically about the Burgess shale. And, I think there's some controversy that surrounds that book, which makes it even more interesting. So sometime 100 years ago, this is 2022, 105 years, 110 years ago, 108 years, something like that. There was a guy named Walcott, if I remember correctly, who was at the Smithsonian maybe, and he went to the Canadian Rockies and discovered this fossil find, which is full of exotic organisms. Like the one in part B, you see it has 5 eyes, and that's OPABINIA regalis, as you can see here. So there's this fossil. Let's give you a sense on the left of its size, which is comparable to a human torso, something like that. And there's many things to be said about the existence of compound eyes in the fossil record. But when I show this, it's just, once again, it raises questions, about counting. How does the number of segments in the body plan arise, and so on. We'll touch on this, but there's a really interesting paper you can check out called "Control of Segment Number in Vertebrate Embryos," and I think that the question of number of somites, which is related to the number of vertebrae that we have, is something that it's hard to take for granted. So I think we'll probably find a way to make contact with this subject in the context of zebrafish later in the next couple of weeks, is my hope. So here is kind of a recap of some of the really interesting and bizarre cells that one can imagine seeing out in the world with a microscope. And yeah, the radiolarians, the hair cell, truly one of my favorites. Those things are just kind of hard to digest. So this is showing you the stereocilia on a hair cell. And you could imagine carrying out a series of measurements on n of these cells and trying to really understand something about the nature of their regularities. I think it's very cool. The retina is another wild and really interesting example, and the retina is populated by these photoreceptors, and I'm just super excited about the nature of the outer segment. I think this came up earlier when I showed you Little's theorem, and having to do with the shedding of membranes off the end of the outer segment. But again, I'm just showing this here as an example of this notion of endless forms, most beautiful, and then also as a prompt, as a provocation. Just because you can look at this in an electron microscope doesn't license us to say to ourselves, yeah, sure, there's 1,000 membranes stacked, sort of like pancakes, and they're spaced by about 25 nanometers, and they're full of rhodopsin, and yeah, sure. No, no, that's not sure. That really calls for scratching our heads. And I would say the same can be said of organelles. There's this exquisite structure associated with the various organelles that are found within a cell, whether we're thinking about the nuclear membrane and its coupling to the ER, or whether the ER and its coupling to the Golgi apparatus, or the existence of the mitochondria, and so on. So, like I mentioned earlier, Wallace Marshall is a scientist worth knowing about. There's some lectures of his you can find online, and I think it's a very good reminder of not being seduced by the myth of the cell. Different cell types are completely bizarrely different, and his favorite organelle is the NEMATOCYST, and that's something that I think about because I'm interested in stinging organisms in the ocean. So, this specific kind of cell is basically like a jack-in-the-box. It's a coiled spring, if you like, that's permits itself to deliver a stinger under the right circumstances. And so, you'll find this in the context of the cnidarians, which, if I think the spelling is CNIDARIANS. He and I have this, we have this laugh about AP biology, Wallace sent me a text one time showing a picture of his kid having to color in the organelles in a cell, because I was saying, to me, this notion of, just sitting there and kind of mindlessly coloring organelles in some picture of a cell is, maybe not giving us the right sense of wonder about the facets of the amazing organization of these objects and where they might come from. How should we think about that? So, a little over 100 years ago, Darcy Thompson wrote this book on growth and form, which I think was and is very influential and provocative, and in a way I would say perhaps it raises more questions than it answers, but it raises the right kinds of questions. Like, what about all these regularities? And I guess one of the things that I wanted to comment on is the shape, size, and function are coupled in very interesting ways. And, Galileo made this remark: I believe that a little dog might carry on his back 2 or 3 dogs of the same size, where I doubt if a horse could carry even 1 horse of his own size. And there's a really interesting story about how Galileo got onto this track of trying to think about beam theory, which I find, bizarre. When I say beam theory, I mean one-dimensional elastic media, which you see here. And the reason he got to thinking about it was that he was curious whether the description of the inner circle, the structure in Dante's Inferno, could make sense. He tried to actually analyze from a structural mechanics point of view whether that world would make sense, and I think that's really quite amusing. And later, he came back to the question. He wasn't fully satisfied with the way he had answered it when he was thinking about Dante's Inferno, and got to thinking about animal legs and buckling. So buckling instability. And this leads to something we might talk about, which is, how does the cross-sectional area of a bone in a leg scale with the mass of the organism? And the scaling is, not, I don't know, maybe I shouldn't use the word obvious, but it's not obvious. And, we have to pass through things like Euler's treatment of beam buckling, which is a really, really great subject where, and we'll think about this in the context of folding. So the idea is that, if you push from the top on a straw, most of us are familiar with the idea, if we push hard enough, at some point the thing will buckle. And so that's certainly pertinent to the question of how much weight a leg can support. So some of the things we're going to need to understand are geometry changes. I've already hinted at this. So there's sort of areal changes, extending, looping, and coiling, branching. And then even more provocative are topology changes where, the number of holes or handles in a given structure changes over time. So, I'm a little reluctant to show this slide, but I think it's something that just drives home the point that you have these elements from the periodic table, and they assemble into molecules, and those molecules themselves can join together in order to form structures, which we call cells, and then cells can come together to form things we call tissues and organs and so on. And this Paul Weiss 1962 thing shows, if you take an intact embryo and then you grind it up, again, it's really kind of gross, but you grind it up, then you might be able to fractionate it into things of different density, but you're never going to get a chick embryo back again. And so the question we're going to ask is, what kinds of principles can we write down in order to investigate the origin of pattern? And so this is my preface, this is my introduction, and what we're going to do is we're going to examine two principal paradigms. One of them is the so-called positional information idea, which was championed by Louis Wolpert, and then we'll think about the Turing instability, which was developed in one of the last papers of Alan Turing. And those two ideas will be juxtaposed, and we'll find that a modern champion of this stuff is James Sharp at the MBL in Barcelona, who I think really has very interesting things to say about how the positional information idea and the Turing instability idea might be working together to give rise to the kinds of patterns that I've talked about today. So that's the end of my intro.